Swayam Prabha. Digital India. Educated India.
Good morning and welcome back to lecture number 13, part 1 on the topic expansion devices. This is the last topic in the module number 2. In module number 2, we have been discussing about the major components of a conventional vapor compression refrigeration cycle. There are 4 major components: compressor, condenser, evaporator and expansion device. We have already seen the different types of compressor, condenser, evaporator, the construction, their construction along with the working principle. And we have made some comparison between the different types, and also we have solved quite few numerical problems. Now let us move to the fourth major component, that is the expansion device. Primarily the function of expansion device is point number 1. It regulates the flow of refrigerant from the condenser to the evaporator and also the amount of refrigerant circulated in the cycle. And second one is it maintains the pressure difference between the high pressure side and the low pressure side. The high pressure side is the condenser and the low pressure side is the evaporator. So it's a device used to regulate the correct flow of refrigerant to the evaporator, because that will decide the quantity of refrigerant that has been drawn by the compressor. And the second function is maintains pressure difference between the condenser and the evaporator. You see the classification of the expansion devices. It is primarily classified into 2 major categories. One is fixed opening, another one is variable opening. When I say fixed opening, the area of the opening, that is the orifice opening, that's a fixed one. It is not a variable one, as the name indicates. There are 2 types in that one. One is orifice type, another one is the capillary tube. And under variable opening type, we have got 4 types of expansion devices: automatic expansion device, thermostatic expansion device, electronic expansion valve, and float type valve. Float type valve, that is both on high side and low side, that is called high float valve and low float valve. Let us see the construction and the working principle of a capillary tube. This is the simplest form of an expansion device. So it is a tube of length. Normally it is the length is in the range from 1 meter to up to 5 or 6 meters. So the tube length is 1 to 6 meter. The diameter, it has a constant diameter. The diameter is about half a mm, that is 0.5 mm to 3.5 millimeter. So the refrigerant which is coming from the condenser, it is a high pressure liquid refrigerant. Here the high pressure liquid refrigerant enters and after the throttling process, the liquid refrigerant leaves as low pressure, and here it is low pressure liquid refrigerant. How does the pressure drop occurs in a capillary tube? There are 2 reasons for the pressure drop which occurs in the capillary tube. Number 1, the working fluid, which is the refrigerant, it has to overcome the tube wall resistance due to friction. So let me write here itself, pressure drop occurs due to two reasons. The first one is due to the tube wall or frictional tube wall resistance. Frictional tube wall resistance. The working fluid has to overcome the tube wall resistance due to friction. And second one is what happens when the liquid refrigerant, high pressure liquid refrigerant, when it is entering this one, sometimes some portion of the liquid get flashed into vapor. That means after flashing, it will be a combination of liquid and vapor. That is a mixture of liquid and vapor. So what happens when the density of vapor is less than density of liquid? Density of vapor is less than the density of liquid. So as the liquid refrigerant is flowing inside this one, the average density also, the density of the refrigerant across this one reduces. So we know that m dot is equal to rho AV. The mass flow rate, the refrigerant is same. The diameter of the tube is constant. So the area will remain the same. So M and C are constant. This is constant and A is constant. The density of the vapor, that is the average density, will be less. So what happens, due to which the velocity will increase. Velocity at the acceleration of the fluid, working fluid, will increase. When the velocity increases, then the pressure drop occurs. So here what happens, since m dot and A are constant, when rho, this is the average density. When rho decreases, therefore velocity V increases. Due to this, pressure drop occurs. Let us see the salient features. And before seeing the salient features, the mass flow rate of the refrigerant, it is directly proportional to the delta P, where delta P is the difference in the pressure between condenser and evaporator. So now, as if the pressure difference between the condenser and the evaporator is more, then m dot R will be more. And if the pressure difference is less, the mass flow rate also will be less. So when the load increases, evaporator temperature increases. When the evaporator temperature increases, the evaporator pressure also will increase. And if P is increasing, this difference will come down. P decreases. If this term is increasing, the difference will come down. M dot R decreases. decrease. That means the quantity of refrigerant that is circulated by the capillary tube to the evaporator is less than the amount of refrigerant that is drawn by the compressor. Let me repeat. The quantity of refrigerant liquid that is fed by the capillary tube to the evaporator is less, because when the evaporator pressure increases, delta P decreases, m dot R decreases, because both are directly proportional. So the quantity of refrigerant is supplied to the evaporator is less than the amount of refrigerant that is drawn by the compressor. So due to this, the starving problem arises in the evaporator. So this results in, that means mass flow rate of the refrigerant supplied in the capillary is less than mass flow rate of refrigerant that is drawn by the compressor. CO stands for compressor. So this could result in starving issues in the evaporator. Now let us see what happens when the load decreases. When the load decreases, evaporator temperature decreases, which will reduce the evaporator pressure. When in the delta P, Pc minus Pe, when Pe decreases, the difference will increase. Pc minus Pe increases. Since m dot R is directly proportional to Pc minus Pe, that is delta P, therefore m dot R increases, which means the mass flow of the refrigerant supplied by the capillary to the evaporator will be more than the amount of refrigerant that is drawn by the compressor. So let us write this one. CO is, let me write in this corner symbols. CO means compressor. M dot R means mass flow rate of refrigerant. Mass flow rate of kg per second. And Pc is the condenser pressure. Pc is, let me write it here. Symbols. Pc condenser pressure. Pe evaporator pressure. Tca and Te are condenser and evaporator temperature respectively. Under this condition, the amount of refrigerant fed by the capillary to the evaporator is more than that is required for that could be drawn by than the amount of refrigerant drawn by the compressor. So here what happens? The refrigerant will get accumulate in the evaporator. Refrigerant will accumulate in the evaporator. So due to this, evaporator will be flooded with pool of liquid refrigerant. Flooding, evaporator, flooding will occur in evaporator. So, there is no balance between the amount of refrigerant in both these conditions. There is no balance between the quantity or amount of refrigerant that is supplied by the capillary tube to the evaporator and the amount of refrigerant that is drawn by the compressor. So, there is no balancing. There is a point called balance point, which indicates that correct amount of whatever the amount of refrigerant that is required for the required to be drawn by the compressor is supplied to the evaporator. So, whenever there is a flooding in the flooding of refrigerant, that is the evaporator is flooded with pool of liquid refrigerant, there are chances that it will overflow. The refrigerant will overflow. It could overflow, and there are chances of could damage the other components. So, neither of these two conditions, the operating conditions, is technically feasible. So, there should be a balance point so that correct amount of refrigerant is supplied by the capillary to the evaporator, which could be drawn by the compressor. Okay, so in this case, this is starving, this is flooding. Let me write flooding issues. Flooding issues. It is the simplest of the expansion devices among all the expansion devices. It is very cheap. Normally, it is a long tube with narrow diameter. Normally, the diameter is in the range from, say, less than 1 millimeter up to 3 or 3.5 millimeter. And the length could vary from 1 to 5 meter. 1 to 5 meter. So, let me write here. Diameter varies from diameter or bore 0.5 to 3.5 millimeter, length of tube 1 to 5. It is connected directly from the condenser to the evaporator. Since there are no moving parts, it does not require any maintenance. The drawback in this device is it cannot adjust itself to varying load in the evaporator. The area of the opening, that is a fixed one, it cannot be changed. Chances of clogging issues. That is, sometimes if water vapor is present, or if the tube contains air, which if the air is humid, it contains moisture, or the dust particles from the air, dust or dirt particles, it could get accumulated inside the tube. Since the diameter is very, very small, and there are chances of clogging issues. It could affect the flow of liquid from the condenser to the evaporator. So, that is the clogging issues. Plugging issues in the compressor. Critical charge has to be used due to flooding issues. Critical charge, if we have flooding, evaporator is flooding, then the liquid refrigerant that is overflowing, it will overflow from between the portion from evaporator to the compressor. So, we do not have that one, a balance point to be there. For that, a critical charge has to be used due to flooding issues. Critical charge is the correct, it is the refrigerant level, amount of refrigerant in the evaporator up to the brim, up to its brim. It will not, once we have a critical charge, the liquid refrigerant will not overflow out of the evaporator. And this is suitable for hermetically sealed systems. Let us move to the second type of expansion device. This is a variable opening type, automatic expansion valve. So if you look at this one, there is a inlet portion to the wall where the high pressure liquid refrigerant comes from the condenser, refrigerant from condenser, refrigerant, let me write high pressure liquid refrigerant from condenser. And this is the low pressure liquid refrigerant which is supplied to the evaporator. Low pressure liquid refrigerant to evaporator. So if you see, there is it consists of a needle which, according to the position of the needle with respect to the orifice, the location of the orifice is fixed. There is an adjustment spring. Two types of springs are there. One is an adjustment spring, another one is a follow-up spring. Follow-up spring. So let us see the forces. Before that, there is a diaphragm. Sometimes it is called as bellows, and there is an adjustment screw. Let us see the forces which are acting. There are four forces acting. Forces acting on automatic expansion wall. If you see this one, there are four forces. Forces due to adjustment spring, atmospheric pressure, follow-up spring, and evaporator pressure. So, if you see the diagram, this is the pressure force acting per unit area. So, I have used the letter capital P. Pressure due to adjustment spring. Okay, so PAS. Pressure due to adjustment spring. Next one is PA, that is atmospheric pressure. Atmospheric pressure. Next one is PE is evaporator pressure. And PFS, pressure due to follow-up spring. This is adjustment spring. Pressure due to follow-up spring. So here, the forces will be balanced when the summation of PAS plus PA will be equal to the force which are acting on the upward direction, sum of the forces which are acting on the upward direction. So these two forces are acting in the upward direction. So this is the direction. So these two are acting in the upward direction. Upward direction. And these two forces are acting in the downward direction. I mean, it is acting from down. Downward direction. So if you take this one, PAS plus PA If it is equal to PFS plus PE, then the forces are balanced. When the forces are balanced, the forces are balanced. Now let us see what happens when the load increases. When the load increases, evaporator temperature will increase. Evaporator temperature will increase. Evaporator pressure will increase. If evaporator pressure increases, then this term will increase. Therefore, P of Fs plus PE will increase. If it is increasing, the right hand side will be more than the left hand side, or therefore, so this implies PFS plus PE is greater than PAS plus PE. PAS plus PE. Or in other words, PAS plus PE is less than PFS plus, this is PA, PAS plus PA. So when this force, the summation of these forces is less than PAS, the sum of the force due to adjustment spring and atmospheric pressure will be less than the summation of the force which is acting in the downward portion of the diaphragm. So this acts on the upward of the diaphragm. This acts downward of the diaphragm. Let us see what happens when the load decreases. When load decreases, the evaporator temperature will decrease. Evaporator temperature will decrease, which will decrease the evaporator pressure. Evaporator pressure will decrease. When the evaporator pressure decreases, this term will decrease. The summation of force due to follow-up spring and evaporator pressure will decrease. So this will PFS plus PE will decrease. When this is decreasing, this term will be less than this one. Therefore, PFS plus PE will be less than, this implies will be less than PAS plus PA. Or in other words, the summation of the force due to adjustment spring and atmospheric pressure will be more than the sum of the forces due to follow-up spring and evaporator pressure. So let me mention here in one corner, arrow mark, this means increases, this represents increases, and this represents decreases. This represents decreases. So here, when the load is more, the refrigeration load is more, the forces which is acting on the top portion or the on the upward portion of the diaphragm, that is PAS and PA, will be less than the other two forces which is acting from the downward direction. Similarly, when the load decreases, the forces acting on the top portion will be more than that of the forces which are acting in the downward direction. So, I will stop at this point. I will be continuing this in the next lecture. Thank you.